anytime that I'm trying to compute the limit as x approaches some value a, see there's the a? Is that too small? Yeah. Let's zoom in. So a here is equal to 1, right? What I'll do is I'm going to take that 1 and I'm going to plug it in. So the first thing I try, I do 1 minus 1 over 1 squared minus 1. And I get a 0 in the denominator, but I also get a 0 in the numerator. Okay, and as I said before, that's indeterminate. And what's it mean? There's still hope that maybe we can compute the limit. So I try again, and I think about my algebra that I've learned, and there's something about that denominator that your algebra instincts tell you you just want to do. And what is it? Yeah? How? X plus 1, x minus 1, right? We want to factor it. You have a good algebra instructor that told you that at some point. So the x minus 1's cancel. And so now I'm computing the limit as x approaches 1 of 1 over x plus 1. Am I really allowed to do that? Will this limit be the same as this limit? Well, the answer is yes. There's a theorem in the book that says so, and a theorem is something that can be proven. All right? I guess what you might ask is, so there's your answer, 1/2. Oh, yeah? Well, then you can't see anything. But there you go, 1/2. Is this okay? That's why I wish this screen would show up for me, and right now it's not. I need a tech guy in here again. So, what does this mean? This means that we can compute a limit if we have a factor that we can cancel. If you think about the two functions, and if you were to graph the two functions, you'll get exactly the same graph except for one thing. You know, if I graph, maybe I'll try it for you. Actually, let's graph the second one. Since the second one gave more people difficulties, let's do that. So we have x cubed minus 8 over x minus 2. Let me pull out my calculator, huh? There it is. So if I graph y equals, and let's see, I'm going to need to open some parentheses for the numerator. And let's do x caret 3 minus 8, close parentheses, divided by, open parentheses again, and I do x minus 2. And as far as the window, I'm just going to hit zoom and then standard, which is choice 6. That'll give you a 10 by 10 window, or negative 10 to positive 10. Well, there it is, huh? Really? Yeah. Funny, what's that look like to you? A parabola. Is it a parabola? Is that the equation of a parabola? Well, almost, actually. The answer is it's almost a parabola. What this says, remember, is x cubed minus 8 divided by x minus 2. Notice I said divided by. That's what the fraction bar means. So actually, one way to do this problem, again, if I plug in 2 over 2, what do I get? That indeterminate form again. So maybe there's something you can do. The difficulty is, can we factor x cubed minus 8? There was a group in the back, they had the computer, they Googled, how do you factor a difference of cubes? There were a couple groups that remembered. And then there's other ways to proceed too. Anybody do something different to get the answer here? Go ahead.
Synthetic division.
Synthetic division. How many people remember synthetic division? That's not enough. I'm going to go over it. Okay?
Thank you.
Here. X cubed minus 8 divided by x minus 2. That's what it really says, right? We want to, if we can divide by x minus 2, then what we'll be able to do is we're going to rewrite the numerator as x minus 2 times whatever the quotient is. Does that make sense to people? We hope we can do this because then what? Then what are we going to do? Cancel. Do you guys understand the idea? Now, how do you do this? Well, one way to do it, x cubed. Remember polynomial long division? Raise your hand if you think you've seen this before. Polynomial long division. Now, if you haven't, just trust me, it can be done, but it's going to take more time than I want to do. I want to go to synthetic division. Give me the name again. Sam said, let's try synthetic division, the fast way of doing this. The fast way of doing this is you just write down the coefficients. 1, 0, 0, and negative 2. That's all I need. Because who cares what these things are called? I'll deal with the variables when I'm done. Now think about when you do long division. You put the number up there, and what's the very next thing you do? So you say x squared times x would be x cubed, right? I multiply. You guys with me? And after you multiply, what's the next step in long division? I can't believe I'm reviewing long division. Subtract, right? Multiply, then subtract. Well, when you do synthetic division, to speed that up, instead of subtracting, we know in algebra we can add the opposites. So in my little box that goes on the side here, instead of putting negative 2, I'm going to put a positive 2. And that kind of takes care of the subtraction. And now all you do is you add and multiply. 1 plus 0 is 1. 2 times 1 is 2. 0 plus 2 is 2. Am I going too fast? Yes? Am I going too slow? You're going just right, Paul. All right, I'm trying. 2 times 2 is 4. 0 plus 4, 4. What's next?
8.
2 times 4 is 8. Negative. This didn't work.
Oh, 0, negative 2 instead of negative 8.
Oh, thank goodness. It's not negative 2. It's actually negative 8. And since this is a negative 8, what happens now? When I add those, I get 0 as a remainder. Okay? So now what's the answer? X cubed minus 8 divided by x minus 2. You get it from here. This is the remainder. That's the remainder. That's 0. Okay? And so my answer would be x squared, and then what? Plus 2x plus 4. All right. So we got it somehow. It's a lot of work. Once I get all that, okay, the x minus 2's cancel. And so now, can I take the limit of the red polynomial? Well, yeah. How do you do it? Plug in the 2. So I get 2 squared plus 2 times 2 plus 4. So 4 plus 4 plus 4 equals 12. And actually, I should be able to see that on my picture if I look carefully. Let me turn the calculator back on. Of course, 12 is off the map. Remember, I'm only going up to 10 here. So let me change the window. Instead of going from, for the y's, instead of going from negative 10 to 10 for the y's, let's go from 0 up to 15, like that. And let me graph it again. So it is a parabola. And as I'm approaching 2, let's see what happens. If I hit second, oops, sorry. And I can't do it because we don't have a screen. It's kind of annoying. I quit. Anyways. I'll show you that one more time. If I hit the graph button again, or if I hit the table, see, the only place that it's undefined is right here at 2. But if you had the actual parabola, you would put a 12 there, and that would work. Matter of fact, on the other side, you have a 12. See it? By symmetry. It's just there's a hole in the graph where you get that 0 over 0. Guys have any questions on that? Yes? Give me the name.
Matt?
Matt, go ahead.
This is for like future reference, but L'Hopital's rule work for this since it's 0 over 0?
So what does L'Hopital's rule say?
If you had 0 over 0, you can use the derivative.
You can do the derivative. Now, this is no fair because half the people in the class have never heard of a derivative because they've never taken calculus. That's what I'm about to teach. Yes, it works. It's kind of like using a sledgehammer to put a nail in, you know. You can do it. It works. You don't need it. But yes, if you've already taken calculus, there's faster ways of doing it. Yeah. Other questions? I'll have to show you guys L'Hopital's rule after I teach you how to take derivatives. I'll promise to do that. Okay. Actually, that's been recorded. So the third one, see if you can discover the limit as follows. Well, part A, you plug in any of these things, what do you get? You get 0. Because like when you do 1/2, right? Let me zoom in so you can see those fractions a little more clearly. When you plug in x equals 1/2 into sine of pi over x, you're taking the sine of 2 pi, right? Or when you plug in 1/4, that's the sine of 2 pi. We're zoomed in too much. When you plug in 1/4, you're taking the sine of 4 pi. And the sine of any even number times pi is always going to equal what? 0. So you could imagine someone makes a table. And they say, okay, guys, what I'm supposed to do is find the limit as x approaches 0. So I'll take some fractions that are starting to get close to 0. 1/2, 1/4, 1/8, 1/16. And they do that, and they keep getting back 0, 0. And they say, aha, what's the limit? The limit might be 0. And then you go to part B. Now what happens when you plug in 2/3 for x? Well then, this one, what you're actually finding the sine of is 3/2 pi. Now what's the sine of 3/2 pi? -1. And when you plug in 2/9, you find the sine of 9/2 pi. And what does that equal? Let me think. I have to think about that one. Because what's 8/2? 8/2 would be 4 pi. And so that would be pointed where? There's 2 pi, there's 4 pi, right? That's 8/2. So another pi over 2 keeps me up here. So I think this one is +1, right? Am I right or no? Either way, I think what happens here is you get -1, +1, -1, +1. It kind of, a beautiful little pattern emerges. But the point is, are we approaching a single value as we go towards 0? No. So I guess, can you discover the limit? Well, the limit doesn't exist, so the answer is no. In spite of what part A does, that does not, making a table doesn't prove you have a limit. That's my point I'm trying to make. Guys with me? So, it's one of the reasons we need to learn other analytic techniques. And that's one of the reasons I better zoom out again. Okay. Here are some notes from, well, a different book, but same idea. How to evaluate limits analytically. We want to talk about properties of limits. Strategies to find limits. Now, here, you guys, look at this third bullet point for today, what I'm trying to do. Evaluate a limit using dividing out. I don't have to do that. That's what you just did. When we say dividing out, what they mean is factor and cancel. I think you guys understand that just from the group work. This other one I should still do, rationalizing. So I want to give you an example where how you would compute a limit like that. And then we're going to talk about a theorem called the squeeze theorem, which is an interesting theorem, and we'll get to that also. That was mentioned at the very end of the reading, I think. So, moving on. What are well-behaved functions? And there's a lot of blah, blah, blah. There's a highlighted word here, direct substitution. What does that mean? Over on the board we said put what in for x? Put the A in. I think here it's a C. But there's a name that you guys should know. And our book decides to wait until section 6 to give you that word, I think. But I'm going to give it to you now. A function that is well behaved like that at a certain point, we use the word continuous. How many people have heard the word continuous for a function before? Only some. Okay. So the word continuous, you know, when let me do this. When I give the definition of continuity, if I'm teaching an algebra class, I'll tell people that continuous, I'll say the idea is we can draw the function without lifting our pencil, whatever that means. That usually gets the idea across to people. So, in the example I just had, we had a parabola, but it had a hole in it, right? And so this hole is an example of a function which is not continuous at x equals 2. Okay? Not continuous at x equals 2. And the definition of continuity, okay, as I said, we say f of x is continuous at x equals c if the limit as x approaches c of f of x is equal to what? F of c. That's going to be what we want for continuous. And I know we used a on the board before. Okay? Remember, the example that I had from the group work was this function. F of x equals x cubed minus 8 over x minus 2. That's the function which is not continuous at x equals 2. I'm going to say one more thing about the function. It is continuous everywhere else. Does that make sense to you guys? So if I said, hey guys, let's compute the limit as x approaches 9 of x cubed minus 8 over x minus 2, how would you do it? What would you do? Plug in the 9. 9 cubed minus 8 over 9 minus 2, whatever that equals. That's the answer. Because everywhere else, the limit will be the same as the function. So you always try that first. Substitute it. And then if it doesn't work, then maybe sometimes there's something else we can do. Okay. Scooting right along. Let me come back to those theorems. Well, they're numbered different in your book anyways. Your book has these things they call limit laws. And they're going to prove them for you later. Okay? We kind of don't have that technique yet. Let me come back to this. Let me move right along. This problem is very similar to what you had on your group work. I want to skip it. This is the one I want. Let's try this one, guys. So we're going to try and compute the limit as x approaches 3 of the square root of x plus 1 minus 2 over x plus, oh no, x minus 3. Okay. So I wrote the problem down. What's the first thing I should try? Yeah, always try substitution. I mean, if it's continuous there, then you're done, right? But I can see it's not continuous there because, well, 3 minus 3 in the denominator is going to be 0, right? But I should also check the numerator. The square root of 3 plus 1 minus 2. What's that give me? It does, right? Because you get the square root of 4 minus 2. You do get 0 over 0. So we have hope. Maybe there's something I can do algebraically to the function. So what do? Anybody get this from the reading? Oh, you have it?
Did you use the reciprocal, the numerator? So you do, square root of x plus 1 plus 2?
Plus 2, yeah. So the word that we're going to use for that, okay, this is an old trick. You might remember multiplying by what's called the conjugate. Have you ever heard of that? We're going to multiply by the conjugate. This is a trick you probably learned in an algebra class. And I'm glad they taught it to you, but then they also taught you something that kind of fails here. How many of you learned that you're not supposed to have a radical in the denominator? Well, watch what happens in this problem. I multiply by the conjugate, and what's that do? It gets rid of the radical in the numerator and puts it where? Which helps. So, yeah, it's kind of funny, that whole thing about no radical in the denominator. I mean, in this case, watch. I'm going to multiply by the square root of x plus 1 plus 2 in both the numerator and the denominator. Okay? So watch how this works. We will do the limit as x approaches 3. And let's not really multiply out yet. Let's keep this as x minus 3 in parentheses times the square root of x plus 1 plus 2 in parentheses. But now the numerator, well, what happens here? Well, when you multiply conjugates, it's basically two binomials, right? And you do first, outer, inner, last. And when you do the first, you're doing square root of x plus 1 times square root of x plus 1, and what do you get? You just get x plus 1. Because the square root times the square root gets... You guys with me? Okay. So I just get x plus 1. That took care of the first. And now I do the outer, and I get plus 2 square root of x plus 1. But I'm not even going to write it down. Why? Then you're going to get... That's the idea of conjugates. You're going to get minus 2 square root of x plus 1. That's why the radicals go away. And so what's the last thing we have to write down? Minus 4, because negative 2 times positive 2 is negative 4. And one question you might have is, did this help at all? Well, it did. How come? What do you have in the numerator? See, you have x minus 3. Lucky. Well, it's kind of by design, this problem. What happens? X minus 3's cancel. So we don't have to evaluate this limit. What we'll do instead is the limit as x approaches 3 of 1 over the square root of x plus 1 plus 2. Now that's 1 over, when you plug the 3 in, you get the square root of 4 plus 2. So that's 1 over 2 plus 2. 1/4 is the limit. Okay? So if you take the original function, I cannot substitute in a 3. But I can compute the limit. The limit exists. There would be a hole in the graph right at 3 comma 1/4 if I were to graph it. Make sense?